Hello everybody, welcome back. So the first speaker of this session is Faizan Bhat. He'll be talking about bootstrapping string-like models using machine learning.
Thank you, Arka. Okay, this is work done with Aninda, Arnab and Debapriyu. Okay, let's start. Okay, first some experimental data. So, data from proton-proton and heavy ion collision experiments had shown, this was known in the 1960s, that there are hadronic resonances that are generated in these hadronic collisions, and these hadronic resonances, they form a family of higher mass, higher spin particles which seem to lie on a linear line. This is what was called the Regge trajectory. Here I'm showing you the Regge trajectory for rho and omega mesons, which are the lightest particles in the family, and they have a mass of 1 GeV square and a spin 1. But there are other members of the family with higher masses and higher spins, which seem to be linearly connected to these lightest rho and omega mesons. And this was called the linear Regge trajectory, and it was parameterized like this, where alpha naught is the Regge intercept and alpha prime is the Regge slope. Okay, and people were trying to come up with models which would fit this data. The problem with having higher spin resonances is that if you just look at the tree level, at tree level, if you have an exchange of a particle of spin j and mass mj, then in the T channel, for example, you will have a pole at mj square, and the residue at the pole is expected to grow as s to the power j. Now, if you truncate this sum to some j max, then the amplitude at large s is expected to grow as s to the power j max. Okay, so this, for large j max, this growth is too fast at large s. There are unitarity bounds on how fast an amplitude can grow at large s, and this violates those bounds. So you need a way to not have these models of hadronic resonance violate unitarity at large s. And a simple way of going, by passing this constraint is that you don't truncate in j max, you consider the infinite sum. And if you have an infinite sum, it's possible that an infinite sum of polynomials gives you something which is softer than, which is less divergent than any of the polynomials. For example, the exponential function is an example. Okay, in 1968, Veneziano actually proposed such an amplitude which has these features. It's called the Veneziano amplitude. Alpha prime is the Regge slope, which I'll take to be 1 throughout. Okay, so this is the Veneziano amplitude. It has certain properties. There are poles in S which are infinitely many because of the gamma function, which you can see here. So there are poles in S and T because this is symmetric in S and T. So you have this amplitude has a property called duality, which means you can expand this amplitude completely only in the terms of its poles in S and T channel. Here I'm showing you the T channel expansion, and nothing else. Usually you would expect there to be pole terms and some non-singular term, which could be some polynomial. But in this case, that term doesn't appear. It's completely only poles. And the residue at the pole is S. If you see the residue, it's a polynomial which grows as s to the power n minus 1. And as I showed you, if the residue grows as s to the power j, then the highest spin particle that is getting exchanged of mass mj has spin j. So in this case, the highest spin particle getting exchanged when a particle of mass n or n by alpha prime is getting exchanged has spin n minus 1. So you see that this amplitude actually has this, it exhibits Regge trajectories of this form. So this is the linear relationship between j and n, and the particle with the highest spin has j n minus 1, which is called the leading trajectory, and there are particles with lower spin and the same mass, they call subleading Regge trajectories. So this amplitude combines all the higher spin particles, and interestingly at large s, it grows as s to the power minus 1 plus t. So this is called Regge behavior. So you can see for t negative, it doesn't blow up. So dual resonance, these are called dual resonance models because they satisfy this property called duality. And dual resonance models basically taught us how to include infinitely high spin particles in an amplitude without violating unitarity at large s, which this tells you, because this for negative t, it doesn't blow up. Okay, so these kind of representations of dual resonance models have been known since the 1960s. But this is in sharp contrast to what you expect from field theory. When you have quantum field theory, you never have just poles in one channel with that express the amplitude. You always, at every perturbative order, you have S channel plus T channel plus some contact terms all together. Such a representation for the Veneziano amplitude was not known till only this year, when Ananda and Arnab, in a now very famous paper where they had this pi formula, they presented this representation for the Veneziano amplitude, or what is now called the open string amplitude. And this this representation, you have some, we call this the field theory representation, because you see there's a pole in S channel and there's a pole in T channel, and there are contact terms which are expected to come from interactions of this form. Okay, and it is manifestly crossing symmetric because the residue at the pole is a function of ST, and this is also ST symmetric. Okay, and there's an extra parameter that you see here, which is lambda, and there's no lambda on the left hand side. So this lambda dependence is supposed to disappear when you do the infinite sum. But if you truncate to some n max, the truncated sum does depend on lambda, and this constraint, lambda independence, is called field redefinition independence. It basically arises because lambda is supposed to be a field redefinition parameter, and field amplitudes are supposed to be independent on the field redefinitions. So that is what this constraint is. Okay. Now this representation is only for the open string amplitude, which is this amplitude. In general, in a unitary theory, in a unitary Lorentz invariant theory, this residue at the pole, this is just a polynomial. This is the Pochhammer symbol. So this is basically just a polynomial in S and T of degree n-1. This polynomial in a unitary Lorentz invariant theory can be expanded in a basis of partial waves. Partial waves are basically Gegenbauer polynomials in D dimensions. So you can expand the residue of the pole in these Gegenbauer polynomials, and the coefficient is called the partial wave coefficient. So the statement of tree level unitarity is that if you do this expansion, these CLNs are supposed to be positive. Okay, so if you, instead of this residue here, which is in this case, if you simply plug in this partial wave expansion, you get, for a general amplitude, you get an expression of this kind. Okay, where if you plug in the CLNs corresponding to the open string, then you will recover this amplitude. Okay, so this is the representation we'll be using going on. So this applies to this class of amplitudes which are called dual resonance models, and we will try to see what is the space of all the dual resonance models, which means what is the possible space of these partial wave coefficients, because everything else is fixed, and the constraints we will put on the partial wave coefficients are these, that they are positive, which is unitarity, and there is field redefinition independence, which as I mentioned is the statement that the amplitude is independent of lambda. So if you take k derivatives, then the amplitude is supposed to be, the derivatives are supposed to go to 0. Okay, so now let me come to the bootstrap part of the talk. So the bootstrap approach is basically, rather than having a Lagrangian and then solving equations of motion and then computing correlators, the bootstrap approach is slightly different. We don't try to solve a theory, instead we ask, if I impose consistency conditions such as unitarity, crossing symmetry, Lorentz invariance, some analytic properties for the scattering amplitudes, how much can I constrain the space of scattering amplitudes? So in this talk, for example, what I will be asking the question is, in the space of all consistent scattering amplitudes that satisfy duality, is the open superstring amplitude special in any way? Which basically means if I take amplitudes which have this expansion, which is parameterized by these partial wave coefficients, is the solution that corresponds to the partial wave coefficients of the open string amplitude, which is this one, are they special in any way? And we'll see that they are special. Okay, so now if you have to place bounds on a space of scattering amplitude, you need to first parameterize that space. So we parameterize the space of scattering amplitudes around the low energy expansion, which is the expansion around S plus T 0 and ST 0. This is the low energy expansion because S and T are small. And these coefficients that appear in the low energy expansion are called Wilson coefficients. So we will be bounding amplitudes in the space of these Wilson coefficients. There's actually also a massless pole, which is here, which I have subtracted off. That's why you don't see the massless pole appearing here. Okay, so what are the constraints we will impose using the bootstrap? We will impose in d equal to 10, because d equal to 10 is the dimension in which open string amplitudes are unitary. We'll impose crossing symmetry, we'll impose analyticity, that the amplitude only has simple poles that is equal to n, and the residue of the poles, these residues, this structure is what the open superstring amplitude has, so we will assume the same structure for the residues, and we will fix this Wilson coefficient and this Wilson coefficient to the open string values. So for the open string, which is this amplitude, if you actually do this expansion that I showed you, you will find that W10 is zeta 3 and W01 is some zeta 4. So once I fix W10 and W01 and I impose these constraints of unitarity and lambda independence, I'm trying to ask what are the possible solutions, possible amplitudes that I can see, and is the open string amplitude special? Okay, and so this constraint, this lambda independence constraint, has to be imposed in some domain in SNT, because it's a function of SNT. So the domain we impose it in is looks like this. It's randomly selected. The one point that I want you to take note of is that there is no, I'm not imposing constraints at large S and large T. This is because at large S and large T, because this is a gamma function, the open string amplitude is huge. And there are some issues that arise from the open string amplitude being huge, which is why we need the machine learning part of the talk. So I'll come to that later, but for now just keep in mind that when we impose the lambda independence constraints, we don't go into the region which is S large and T large. Alright, so these are the solutions we get from the bootstrap. You'll hear more from this in DC's talk. So we maximize basically what we are doing is we are fixing W10 and W01, and we are trying to maximize what is the maximum possible value of W00 given these constraints. Okay, and the maximum W00 happens to be related to the minimum of the entanglement generated in the scattering process. And why this is true, DC will cover in his talk. I'll just show you the results. He'll also show you the similar results. So from the bootstrap, what we get when we minimize entanglement or maximize W00 are these values for CLNs. And if you compare them with the open string values, they're extremely close. So somehow, and this is the leading trajectory and this is the subleading trajectory, leading CLNs and subleading CLNs, and somehow minimizing entanglement or maximizing this Wilson coefficient seems to pick out the superstring amplitude very accurately. In fact, if you plot the solution we get from the bootstrap for some truncated, these are some numerical parameters which you can ignore. So the superstring amplitude and the bootstrap amplitude in fact seem to lie on top of each other completely, up to large values of energy. So when we had fixed these two coefficients, but these two coefficients only fix the behavior of the amplitude in some low energy, low S, low T region. But we see that the minimizing entanglement actually gives you the amplitude up to a larger value of S. Alright, okay. Now let's come to why use physics-informed neural networks to do bootstrap. So the bootstrap problem I showed you now, which was this. These were the constraints, and so here I am imposing the derivative with respect to lambda of the amplitude is small. And by small I mean I basically put a tolerance of 10 to the power minus 9. So the bootstrap problems we discussed till now, in fact all bootstrap problems are either linear optimization problems or semi-definite optimization problems. The one we had was linear. These can be handled extremely well via traditional methods. There's a caveat though. We used epsilon, which is the tolerance for satisfaction of these constraints, because numerically you can never impose exactly 0, you have to set some tolerance. We imposed 10 to the power minus 9 while imposing this constraint in this domain and for these many derivatives. However, truncated to some n max, it is not guaranteed that these constraints will be satisfied to some small tolerance. So if you see this, yeah. So this guy is supposed to be lambda independent only when you do the independent sum. If I truncate to some 30, which I do, no one told me that this will be lambda independent to some very small tolerance. In fact, in regions when the amplitude is big, which is this region, when the amplitude is big, the derivative itself can also be big. So what you really should be imposing more reasonably is not that this derivative is small, rather the ratio of the derivative with respect to the amplitude should be small. Or even better would be if you simply impose m lambda 1 equal to m lambda 2. So this ratio is small. The trouble is these constraints are non-linear in the parameters. Okay, so m lambda is a function of CLNs, and because you have CLNs in the denominator as well, this is no longer linear like this was. And traditional methods that are used, for example, there's a package called SDPB, semi-definite programming for bootstrap, which is traditionally used in all the bootstrap problems. These are not useful because they cannot solve nonlinear problems. This is why we use physics-informed neural networks. Okay, what's a neural network? A neural network is basically a map with several tunable parameters. So in this case, we are trying to learn a function which is a function of two variables L and N. So we will approximate it by some neural network, which is a function of ln and some several parameters theta. So this is the architecture we use. You have you have an input layer which is two-dimensional, 2 neurons, because you're only trying to learn ln n. Then this gets passed to these hidden layers where the learning happens. Hidden layers are basically all the parameters are there, and then it spits out some function CLN. So I have 2 neurons in the hidden layer and 64 neurons in these 2 hidden layers, and 1 output layer with 1 neuron. And for this neural network to learn a broad class of functions, you need to supply some. So this takes in ln n as an input, this neuron, and it spits out some linear combination of ln n plus some bias. This is not very important. And then you have to act that combination by a nonlinear function. So basically, if you don't have nonlinear functions in your fit function, which is your neural network, it won't learn very efficiently. So the nonlinear functions are called activation functions, and the one we use is of this form. It's called the rectified linear unit, and it's basically the maximum of 0 and x. In the final layer, these are the sigmas, ReLUs. In the final layer, I have a gamma. That's because I want my CLN to always be positive, which is the unitarity constraint. So gamma is of this form. So whatever this spits out is x, and then log of 1 plus exponential of x is always a positive number. So whatever my neural network puts out is always positive and unitary. So the total parameters I use in this neural network is 4417. Okay. What else? Yeah, okay. Typically, neural networks that we hear of, they try to find the best fit curve to a given data by minimizing some loss function, which measures. So the loss function measures how well the fit curve that the neural network is learning fits the data, and you want to minimize the loss function so that your best fit curve is the best fit you can have. Physics-informed neural networks are a subclass of neural networks where the loss function also includes some physical constraint terms. So it's not just fitting data, you also have some equations that you want the data to satisfy. And the true solution to these physical constraint equations is learned as the physics-informed neural network updates its parameters every epoch via the gradient descent method. So what happens is basically, initially when it's trying to learn, at epoch 0, when it has not learned anything, it will pick some random values for these thetas, these parameters. And with those random values, it will compute some CLN. Okay, and that CLN will not be the CLN that, for example, in this case I want to minimize entanglement. That CLN will not be the solution to the constraint equations. So what will happen is the loss will be huge. Okay, so let's come to the actual loss function that I use. The actual loss function that I use is so I want to minimize loss. So I will minimize loss by equating loss to the thing I want to minimize, which in this case is the entanglement. So minimize entanglement is equal to minus W0, so maximize W00. So maximize W00 with respect to these constraints. W10 has to be fixed to this, W01 has to be fixed to this, and some additional constraints. So when these three go to 0, these three constraints are satisfied, your loss function is basically equal to minus W00. So if your loss is minimized, your W00 is maximized, which is the problem you wanted to solve. Okay, and at epoch 0, it will take some random values of thetas, compute this loss function, which will be huge, and then in the next step, it will update the parameters in the direction in which the loss function is minimized. And it keeps doing that till it minimizes the loss function up to some tolerance which is specified. And then you say, okay, my loss function is minimized completely, these constraints have gone to 0, and therefore the minimum of my loss function is the maximum of my W00, this % coefficient, and therefore I have solved my nonlinear constraint optimization problem. So the nonlinear part is here, which I'll come to next. Okay, so in the first case, as I said, we want to impose constraints of this form. So I will impose this constraint here of this form. So when we impose this constraint, so you can ignore most of this. When I impose this constraint, the solution that I find basically satisfies the constraints up to some 10 to the power minus 6 here, 10 to the power minus 5 here, and 10 to the power minus 4. And you see that the neural network basically gives you values which are very close to the open string. So it is able to impose nonlinear constraints and get you the correct answer. And in the second case, I impose the ratio of derivatives. In this case, for example, the domain in which I impose, this is the domain in which I impose the lambda independence constraints. And in this domain, there is at least one point when S is 10.4 and T is 10.1. So when S and T are 10.4 and 10.1, the open string amplitude, which you want to bootstrap, is actually huge. And its derivative is also order 1. So this naive constraint that I was putting before, where I was setting this, I was demanding that this derivative is like less than 10 to the power minus 9. This won't work, but the ratio will work because the ratio is still small. So this is an example where traditional linear optimization methods would have failed or would have actually ruled out the open string amplitude. But the physics informed neural network method actually works, and it gives you constraints that are satisfied up to a high tolerance. Okay, so that was it. Thank you. So this is a summary.
Does it work? Yeah, it works. Thanks very much for this very nice talk. It was really very clear. So about these constraints in the bootstrap, they've always tree level, right? And I think so some of these constraints, if you say, well, allow torus contributions or one loop contributions, the constraints in principle, many of them disappear. But it seems to me that your ratio constraints, which would say, well, the tree level must at least be larger than the one loop, could be a way of somehow including loop effects in this way. Right?
Yeah. So the thing is, you're right. I'm only doing tree level amplitudes, and that is because my whole setup is only meant for tree level amplitudes, because the formula that I use is of this form, and you can see I'm basically only picking up poles, simple poles. If you have a one loop amplitude, you have branch cards. Yeah. So then this whole setup will have to be modified to not just pick up the poles from n to infinity. In fact, if you allow loop processes, then this massless pole that I subtracted, this will start contributing, flowing in the loop. Then you have branch cut going from 0 to infinity. So that will be, it can be handled. We are planning to do that next, but it's a much more involved.
Okay, thanks. But nice method.
Any more?
Yeah. You will not get the. So these answers that you're getting very close to the open string, you will not get them. In fact, we have done that, and DC will show you that plot with different W10s and W01s. Yeah, but the interesting point is the only information I required was in the low energy limit, and somehow minimizing entanglement is reproducing all these resonances up to some large value of energy. That is a non-trivial part. I only fix some low energy part, and I'm getting the full amplitude up to a very large value of energy.
Yeah, Yeah, that was one of my questions. Like, what was the last constant? I mean, this derivative constant, d lambda.
Yeah. So you want to know what this constraint is?
Yeah.
Okay. So that would require explanation. Let me.
Okay. Before that, I mean, just make it clear that I use this amplitude. For the amplitude, we just know that this is crossing symmetry. That's all. I mean. And then this is the second constant on that, right? And rest of the constants are on this RHS. I mean, this C's.
Yeah.
Okay.
So this is basically, I mean, we can talk about it later, but this basically follows from the fact that this follows from locality. So if you have an amplitude, it should not, in this Wilson coefficient expansion, you should only have powers of positive powers of S and T. If you have negative powers of S and T, you can imagine them coming from a Lagrangian which has inverse derivatives. So you don't want a Lagrangian with the inverse derivatives. So here I have not kept those inverse power terms. That is because these constraints are basically exactly setting those negative power terms to 0.
Okay, that's local.
because at this level, at this point, it is not guaranteed that those terms will be 0. So these are called these lambda independence can also be seen as locality constraints.
And I think that question was asked. So this if you have some different structure of this this M, so then I mean in the tree level you have no other structure, right? In the tree
You
level,
only have simple poles on the real axis. Yeah.
that's all.
But of course, if you do loop, then you have branch cuts, and then this formula will change completely. So this formula comes from a contour integral,
Yeah.
and in that contour integral, you only pick up poles. In that case, you will have pick up the discontinuity across the branch cut. I think DC will show you the contour integral as well.